here to show this demo. So this is an old demo from about 10 years ago. That was this thing we talked about yesterday, where we've got we're doing dimensionality reduction on this figure here, and we've split the figure into separate parts. So we've got little latent spaces for each part. But then we have this relationship, this hierarchical relationship, that this latent space controls these latent spaces below, so drawn little lines in to show that. And this is a little MATLAB demo to sort of show what's going on. So for example, this upper body node here is a two-dimensional latent space, and it controls the upper body. So if I'm near the red, that's from the running motion, so you see the running motion there. And then you can see that I'm representing what hopefully you see as I move the cursor around. Let's see if I can mouse it. That below, in the latent spaces below, these latent spaces are a function which has this as an input. So you've got this sort of composite function idea that means that I'm able to control the whole body. If I go right up to the top, now I never get this the right way around. Going the right way around, then you start seeing the warp being reconstructed, right? So everything's moving around approximately where the data was. But if I go off the data, you see some interesting things. So this is like the running motion of the arm here. And then over here is the walking motion of the arm. And of course, now I've gained an ability to interpolate something that's not running or not walking, you know. You can move the legs around in sort of like, funky ways. So the walking sits somewhat within the running on the leg. But you get a sort of idea of total leg motion. So the idea with this sort of model is, because you've got the conditional independencies operating together with the dimensionality reduction, then you're not within the model. You should be able to handle things like someone moving their arm in a strange way as they're walking, you know, because that's the way humans are. But when we did this work, we couldn't, as I said, we did everything by map. So basically, we stacked. It was inspired by work of Jeff Hinton at the time, who was doing stacked Boltzmann machines, and I think I saw him talking about that probably as early as 2001. He was talking about those models. I can't remember. Like I was at Microsoft Research at the time, which was made in 2001, where he was saying, "Oh, well, let's just stack these unsupervised learning modules." So I've got one unsupervised learning module here, which is my restricted Boltzmann machine, and I'm just putting another one on top and another one on top. And then they used that to initialize neural networks and then the whole deep learning. But the original deep learning thing was much more about unsupervised learning, and because the GPLVM was similar, then this is kind of the same thing. But I wanted to put these conditional independencies in. So they're stacked, but with structure. So you've got sort of, this Gaussian process is only controlling these two, and this Gaussian process is only controlling these three, and this Gaussian process then controls the arm. So that was sort of trying to combine these ideas from graphical models with ideas from deep stack learning and dimensionality reduction to get one like this. And this is a model that I think ever since then I've been very interested in, because it seems very powerful. If you can switch on and off these connections, even for different data, then you're doing some interesting stuff. Now, I don't quite know whether it's been very slow to download the talk. Look at that. So I'm going to switch laptops. Because what I'll do now is I'll talk about the sort of modern version of that model. I'll have to come back to this laptop to show you the final demo of that. But where we actually do this and we don't do map learning. So I'm going to get a bit more technical, because I'm going to teach you a bit about the variational approximations we use to do that. But since yesterday, when I asked, very few people seem to have a background in variational methods, I'll try and introduce them fairly slowly. So the objective, and I might run out of time, which is a bit worrying when someone says that at the beginning of an hour and 15-minute talk, isn't it? What I'll try and do, though, is introduce our latest sort of efforts with these types of models. Right. So they're called deep Gaussian processes, and the approach we use we call variational compression. So let's see if I got the right one. So the talk should should be online, but if you'll probably find, like me, that it's a bit slow to download at the moment. So this is much more in line with my research. Well, we started to start on that yesterday, but even more so today. This is sort of latest things we're working on in the group. Oh, confused. So, okay, so I'm going to start with, neural network people tell me this is upside down. This is a deep neural network. Drawing these was the reason I got into the field. They just seemed like a lot of fun to draw. I was really interested in these models in 1995. I draw them this way because I'm going to use it as, I understand why they draw them the other way up. So I'm going to use this model as a latent variable model in the end. So a deep neural network, you have some inputs and you have some outputs, right? And it's just a regression model with some basis functions in between, as I'll highlight in a moment. So they would normally say that you've got the detailed activity is occurring on the inputs, right? And then as you map down, you get more and more abstract things. So in here you get convolutional layers, and down here you get fully connected neural network layers mapping out to some classification. So the features of these things, these layers, tend to be the more sort of abstract features in that sense. So I think that that's, to me, instinctively, you should have the abstract features higher up because they're the higher level ideas, right? And the lower level ideas should be lower down. I draw it this way because in the latent variable case, if these are latent variables, things are the other way around, right? You want the abstract things to be your latent variables at the top, and then you get more and more detailed as you go down until you see the data at the bottom. So for me, this will end up being a high-dimensional data in the end. But for the moment, let's just think of what's really the successful thing that everyone's really excited about, which is just this with convolutional layers. Ignoring the convolutional layers, if we just want to think about what these models are if they're stacking on top of each other, I just think of them as they're just basis function models. So we introduced the basis functions in the first stage. So what we're saying is that these, at each layer, you have some sort of mapping from X to the layer, which is given by a matrix times your inputs, W1. And then you apply nonlinearity. Now, because they're neural networks, that's like an activation function or a neuron or whatever like that. But in statistics, that would just be a basis function. But then the interesting thing you do is you then push them through another set of basis functions again. So the outputs of that, you push them through another set. And then the further interesting thing you do, which you wouldn't normally do in a generalized linear model, is you have many parameters here, and you optimize. Right? So in a generalized linear model, you typically would keep your basis functions fixed. Yeah. But there's no reason you shouldn't. But they all sit within the same class of thing until the output, and I'm just assuming regression outputs because I'm going to compare to Gaussian processes, so we can do classification, but regression is a more natural comparison. So mathematically, this is all we have, right? We've got a set of basis functions coming together. I like drawing that, and you can draw that in Tixi so quickly now. Who uses Tixi? Tixi's so cool. Yeah, you can have it set up to draw those very quickly, much quicker than drawing in PowerPoint. But there's a big problem here, actually, because if the number of nodes in two adjacent layers is big, the corresponding matrix is very, very big. So there's the potential to sort of seriously overfit. And this is why you hear about things like dropout. And then they do these strange sort of things where they take out half the nodes and only train half the network, and then they correct for it. Now, someone's done this. Since I started saying this, I think someone's done this, because I saw a paper that was saying things. But when I first said this, no one had done this. This is a different thing that you could do. So an alternative solution to dropout is, this is a very natural solution to anyone who works with matrices, is to reparameterize W with its singular value decomposition. Now, the singular value decomposition of W is it's a matrix that's orthogonal, a normal matrix, and then a diagonal matrix, which is would be like a bit like the eigenvalues, and then this is like a rotation permutation matrix, another orthogonal matrix. So actually, if you multiply these things two together, WW transpose like we were doing last time, you get U lambda squared U transpose. So this is very similar to decompositions we were using yesterday. But in fact, you don't specifically force that singular value decomposition. What you can do is you can just put in W, you say it's effectively got this structure where it's one matrix times another, where this matrix is K1, which is the input dimensionality, by Q, which is a lower dimensionality, and this is Q by K2. So what this does is, this whole matrix here has K1 by K2 parameters. This gives you a way of parameterizing this matrix in K1 times Q plus K2 times Q. It's a really good trick, and I'm really surprised that people haven't tried it, but I think they have now. So this is a low-rank matrix factorization for the weights, and it's a way of reducing the parameters. So this is what this would look like if we draw it in as a neural network. You've got now intermediate, what you have now is x to these intermediate variables, which is just done by mapping, I think I call these things z, I'm not sure. I probably changed notation a bit. So we're going to some intermediate sort of variables here, and then a linear mapping out. It's like having extra layers of linear neurons, right? But they constrict things. So they sort of bottleneck things as you go down the model. And so if you multiply these things out, you would just get a whole matrix of weights where each line is associated with a parameter, but it would be a constrained matrix. So what this does is it gives you the representational power of the nonlinearity, which is what they really want. What they really, really want. So they want very nonlinear layers, because they're all interested in getting these big nonlinearities in, but they don't really want the parameter size associated with having done that. Now, if they were more intellectually, then they would think about marginalizing these parameters, and that's what we do. But what they actually do is it just turns out it works, and like loads of the research in deep learning is, oh, well, why does that work? Oh, and we'll do dropout, and really clever ideas, and you actually do have to be really, really clever. Like Jeff Hinton coming up with dropout, or, you know, how do you do that? I don't know. How do you just make up algorithms like that that actually work? And he does it consistently. It's not just luck. I mean, he's got a way of thinking. Anyway, it's been said, someone said this once, which I really like. The main point of machine learning as a field is to try and understand what the hell Jeff Hinton is doing. And I think that's a good summary. Certainly it's a good summary of large parts of the field. You know. This is now the new setup, right? So we've got these intermediate variables I've introduced to set. And the reason I'm doing this, as you see, well, they say I've motivated it in terms of a dimensionality reduction, in terms of parameter reduction. But it also has this effect of making me able to write a model, getting rid of the h's, which are just sort of, intermediate parameters, and rewriting a model in terms of z. Now, if you particularly look at these letters, these z's now, what you have is a set of basis functions operating on a matrix times some inputs, which is then multiplied by a set of matrices on the output. So this itself is not a linear model of the type we briefly mentioned in week 1. This is just a basis function model like an RBF or a neural network of any type. And of course, the point is, I showed you already on the first day that if I want, so there's this challenge of choosing the number of basis functions. And I said they want that to be very, very high. And I did the whole walking up and down the stage thing to try and explain how you can get infinite basis functions in there. So if we reconstructed this model in such a way that these models here are now one of those basis function models, we can now substitute in Gaussian processes for that part. Okay, so now we can say, instead of making choices about the number of hidden units in each layer, I'll just go infinite. So we can just say something which I think is much prettier. We can say that, look, we've got this series of functions, where each function we determine to be a Gaussian process. So deep neural networks are this as well, but they don't tend to write it like that, because then you can't talk about neurons and things. You know that. I don't have to do that slide, right? That's Gaussian processes, which you already know about. So that was the first slide I used to try and introduce them. And when I'm giving this talk without having given 4 hours of lectures before, then I would talk about that a little bit. So mathematically, and this is what I really like. So the slides I'm giving you here are a deck of slides that I've given to statisticians and applied mathematicians. Because basically they want to know what's going on with deep learning, but they're like, it's very hard literature for them to follow because it's interesting how much of it focuses on the algorithmics, in terms of like what you do to train the model, right? And this was also true in the 1990s, depressingly so. That people became much more obsessed with making small changes to the algorithm, which they couldn't necessarily motivate from a modeling side. Sometimes they could, sometimes they couldn't. But because so many people were doing it, some of them worked. And I think we're back in that era now, and it's probably okay, I hope it's okay, because we'll move back towards thinking a bit more about the model over time. The field goes through these stages. But it is true that if you go to conferences on deep learning now, that you get a lot of talks that are just like about, oh, here's the original algorithm for optimizing this, and I've changed it in this way to stop the gradients disappearing, or something like that. Which is probably very good work. But at the end of the day, that's not going to take you into new modeling domains, I feel. So we want to do a bit of that. So that's what deep learning is. And a mathematician would immediately then say, well, that's pointless because just write g of x. But there's something that's not pointless about it, and this is something you won't hear pointed out so much by people who are in the deep learning area, is why is this important? Is because this is a setup whereby f is a simple set of functions, and g becomes therefore a more complex set of functions. So that's what you're really doing, right? So stacking these things together is just giving you a new function, but the class of functions of g of x is different from the class of functions of f of x. So there's two motivations that are sensible for deep learning. One is, I do very much, certainly I very much like Jeff when he was speaking about this back in the 90s, the idea that, well, for me I'll have abstract features up here and it'll go, for them there's abstract features here and details at that end. This idea that everything is layered in some sense. In fact, sometimes I talk about it now saying, well, most concepts that humans talk about when we're having intelligent conversations, we establish the layer of granularity we're talking about. Like if I'm talking about what's wrong with the network, I'd say the browser's not working. I don't talk about what's wrong with the cables under the ground or the TCP/IP's failed or something like that. We operate at different layers of granularity, and that's a really useful concept. Okay, so what we're going to do is replace these things here with Gaussian process models. And the reason that that's an interesting thing to do is because it totally changes the properties of the process. So I call this now, so I've named this idea, which is just deep learning, but for statisticians I call it stochastic process composition. Right? So you've got a set of stochastic processes. There are certain properties of the individual stochastic processes, which may not be the properties you want. You can change those properties by composing these processes together. So that's a sort of general way of going to a different class. Stochastic processes are difficult to derive. The Gaussian processes are very special. They have all these properties about consistency and everything else. So to know you're within a valid class of stochastic processes is a little bit of a pain. But by composing in this way, you are within a valid class of stochastic processes that is non-Gaussian. And I'll sort of try and persuade you of that as we go on. So they're beautiful things, Gaussian processes, as we've already seen. And here's a beautiful property. The derivatives of a Gaussian process are also Gaussian distributed. I haven't spoken about this before. The reason is because derivatives are a linear function of the underlying function. So that's sort of very easy to think about when, now I'm going to have to try and remember the formula for a derivative, but it's like f of x minus f of x plus delta x over like delta x, something like that, can't remember. That's a Gaussian process. That's a Gaussian process that's correlated with this Gaussian process, but it's a Gaussian process. So you're just subtracting one Gaussian process off another to do a derivative. It's a linear operation. So the result is a Gaussian process because Gaussians sum to become new Gaussians, right? Same with integrals. Integrals are just discrete sums. So the integral of a Gaussian process is also a Gaussian process. So that's a property of a Gaussian because, because of the basic formula for a derivative. And derivatives are known as linear operators because of that. Now, to convolutions also. So there's lots of elegant stuff you can do with that, which we've also worked on, but I'm not going to talk about. But that's a warning, that's a klaxon. You know, so if the derivatives are Gaussian distributed, that means that you can't get sort of interesting distributions, interesting effects. Like, so here's something that definitely doesn't work. We've already talked about that. Discontinuities. So telegraph noise. So telegraph noise is when you're going along flat and then you jump, and then you might jump and like this. So this thing, what's the derivative distribution of this? It's either 0 or infinity. Right? So if we look at the marginal derivative distribution of this, it's got a spike and then a slam. So anything which has this sort of form with many jumps in it is very non-Gaussian. What this implies is that the marginal distribution of derivatives will also be Gaussian. So they're never going to do anything like this. And that is really a big constraint, actually. It's a massive constraint when you think about it. So that's quite a bad thing. Okay, they're universal approximators. So all functions have support under the prior, but that is really meaningless. Philip Hennick had a really nice example in one of the GP intro lectures. If you watch his one, you'll see lots of cool stuff that's orthogonal to what I say. And one of the things he demonstrates is just how slowly, I think it was Philip's lecture, how slowly you converge to the true function, right? And you converge in a horrible way as well. You do awful things as you're getting more and more data. Where your prior is wrong. So you really want to have a better prior for doing these things. So, so I've covered that. So this is Jen Dai, who's been working with me on improving this. So there's these nice pieces of work doing analysis of these deep Gaussian process models. So Dibonneau and other colleagues, Ryan Adams, Stephen Garamani and others, I can't remember everyone, showed actually that if you compose these stochastic processes, this is why it's a nice thing to do. And I really love this paper. I hate the title, but I love the paper. The title is something like Pathologies in Deep Models. And they're not pathologies, they're good things. So what they show is that you can do analysis of this stochastic process composition, of its derivative distribution, and it becomes more heavy-tailed under certain parametric assumptions about the covariance functions as the number of layers increase. So you can theoretically show that if you want a heavy-tailed distribution, you can do it by increasing the number of layers in your Gaussian process. Simultaneously, the thing they don't point out in the paper, such a deep Gaussian process can also have a Gaussian derivative distribution. Because what you can actually do, so it's kind of obvious that because Gaussian processes can become broadly linear by increasing their length scale a lot, you can just make this function, this function, this function, this function linear, and then you've just got a GP. So you can also revert back to the original model, although it won't do that very much in training because I think it's a difficult optima to find. So actually what they suggested, which is a really good idea, is putting x in at each stage. So f2 of f1 of x plus x, and then f3 of f2 of f1 of x plus x. So reinserting x at each layer, so having skip layers. And that turns out to really help training and practice. Isn't that depressing? As soon as you get into deep learning, you worry about things for helping training. So as we talked about yesterday, and I'm using z here for the latent variables instead of x as we had yesterday, because we're doing this deep thing now, and x are my sort of inputs for the moment. This is the sort of challenge of the Gaussian process, of the deep pushing things through these deep Gaussian processes. We're going from perhaps low dimensional spaces to higher dimensional spaces through a Gaussian process function. And when we put probability distributions through that, they distort and they become intractable. So here's a nice 1D example of that. So this is a Gaussian start. So you can even do you can do these models with one dimension. And you put it through a nonlinear function and you get something that's multimodal and intractable. So that's why we have transitive tractability. So the thing I'm going to sort of talk about next is how we resolve that. So this is this technique we call variational compression, and it's got a long history of different people looking at this area. It's one approach to making Gaussian processes more efficient. So there's a few papers I've mentioned here that lead into it. Ed Snelson, Zubin Garamani's paper on something called the Fitzy approximation. Joaquin Quinonero Candela and Carl Rasmussen did a sort of big review of the techniques. That was definitely state of the art at the time. I sort of did some extra stuff on top of that, and Michalis Titsias, a postdoc of mine at Manchester, he was the person that sort of demonstrated this variational compression idea, although the way I'm going to derive it is more due to work we did on it with James Hensman. So the idea is to move from this, and we use low rank representations of the covariance matrix. And this moves us to, instead of order n squared storage, we have order n m squared computation and order n m in storage, where m is the rank of the approximation that we use. So the rank is given by something we call an inducing variable. And hopefully you get the sense of why we call it that as we go forward. So the inducing variables, why have we started calling it variational compression? Because these inducing variables are a compression of the real observations. So the problem for a non-parametric model is that in order to do prediction, you have to remember everything. Everything you've ever been told, you have to store and remember because it's non-parametric. You've got infinite parameters. You can't store a parameter vector, so you store all the data. So if you think about the Gaussian process prediction equations, they involve y for all your training data and all of x. So as that scales up, that's where you get the n squared scaling. So the idea with the inducing variables is to introduce pseudo-observations which are not the real data, but allow you to compress the real data down. So it's like, instead of remembering, and you can think this is the sort of thing people do in real life, instead of remembering every single step of the way from my hotel to this place here, I remember, I go straight, I start with a gradient in that direction, I get to that point there, I then turn, and then I get to that point there, and then I go straight again. That gives me the entire path with like 4 observations. So you can actually reconstruct all the data by compressing it down to 4 observations. And this is the idea with inducing variables. And indeed, they could be gradient observations, or they could be integral observations, or they can even be observations in the Fourier spectrum. That's an area people haven't explored as much as we'd perhaps like. So conditioning on the inducing variables renders the likelihood independent across the data. So once you've got this set of inducing variables, if you've got them right, it gives you it's not the original likelihood, but something that looks like a likelihood that's independent across the data. And this turns out that we can allow some variational handle of the uncertainty on the kernel as well. So deal with the inputs of the kernel. And this allows us to apply a bunch of interesting scaling approaches. So there's work by Hoffman and Bly and others on stochastic variational inference, which is super important work in scaling up Bayesian models. And that allows us, this approximation allows us to apply stochastic variational inference on Gaussian processes, and that's some work by James Hensman and myself. Yaron Gal and I can't remember the second author, and Zubin, I think, also showed that you can use this for parallelizing Gaussian processes. And Gemma and I, my own group, then also did the same sort of thing, but distributing across GPUs. And the thought is that these ideas take Gaussian processes from a theoretical challenge to applying them to very large data to an engineering challenge. And I think that's true. I mean, we're not quite there yet, so in fact, there's particular implementation details that are tough, and you don't get publications for dirty implementation details. So it's one of those things that takes a while. Okay, so what is variational inference?
So with those methods, on how big data sets can you fit GPs?
Well, the beautiful thing about stochastic gradient descent methods is you don't really ever know you've converged, so you can pretend like you're fitting along 100 billion points. So yeah, you can do that. In practice, what we tend to get problems with is we'd like to increase the number of inducing variables and relocate them better. So in theory it can go very, very large, there's no sort of constraint, but I think where we're seeing problems for very, very large data is you get a problem with that you actually want to increase the number of inducing variables more to reflect the size of the data. And I think the right way of, well, there's lots of ways you can do that. You can get very imaginative about that, but we haven't sort of got too detailed into how we're doing that. And one reason is because I worry that with stochastic variational inference, you don't really have a ground truth. You sort of know, you hope that the updates are right and they're moving in the right sort of direction. So actually we've been much more focused on, turns out the numerics of the parallelization are really, really bad, and we've solved that now. So, but we solved it with a company, unfortunately, so it's not sort of public work. So we solved the numerics of that, and so we want to scale up through parallelization, which will definitely take us to millions, and then that will give us a ground truth in terms of what the model's doing with a certain set of inducing variables, and then we can get out stochastic variational inference and start playing with it and saying, okay, let's try these different things, try these update schedules, make sure we're getting up to where we're getting with parallelization, and then go beyond. So that's our research plan for the next. Yeah, so in theory, many, many millions. In practice, making it performant at that scale, there's lots of engineering questions. Okay, other questions before I sort of introduce variational inference a little bit? Okay. So what is variational inference? Well, it's an approach where we convert an integral into an optimization. And it came into machine learning via statistical physics in the 1990s. So these sort of mean field methods, mean field approximations for spin glasses and these type of systems come in from statistical physics, and there's a lot of statistical physicists that have been in machine learning. People like Lawrence Saul, I think, had a statistical physics background. Manfred Oper. There was a lot of analysis of online learning from statistical physics in the early days, so that's kind of how these methods came in. But there's also a classic example from statistics, and since this was targeted at statistics, I focused on that. Statisticians aren't that aware of variation. That's interesting. So it's a general framework where when you're doing a latent variable model, so you've got your sort of prior of your latent variables, which could be parameters, and then you've got your likelihood, which is a function of those parameters, and you want to get this marginal likelihood so you can optimize over the parameters, because you're being Bayesian about things. But this is not always tractable. But actually, even when it is tractable, people look at a particular approach called expectation maximization. So what we do is we compute typically the log marginal likelihood by looking at the log of that integral. And this is a pain because the log of a sum is difficult to deal with. So actually, what you're kind of interested in doing is converting that into a sum of a log, because they're much easier to deal with, the sum of a log instead of a log of a sum. So how we do that is Jensen's inequality. So I've tried to highlight in blue the log and the sum. So Jensen's inequality is that. Right? So you interchange the sum and the log, and that gives you a lower bound on the log likelihood. But that lower bound can be very loose. So it's not something you would use in practice, because typically you'd find this lower bound very poor. And you don't get very good parameters. I've dropped the conditioning on the parameters on the left. Sorry, I should have dropped it also here. Yeah, I dropped it on the left. So the lower bound isn't very useful. So what we do is we modify Jensen's inequality by, first of all, introducing the variational distribution. And this is, why is it a variational distribution? Well, because what we do is it's something we're going to optimize over. We have full control over this because we made it up. We magically made up by that old trick of introducing Q of Z over Q of Z, right? So that's clearly the same thing, because these cancel. We've invented a distribution, and now we apply Jensen's, but Jensen's is valid. This is a probability distribution, and it's strictly positive. It can come outside the log along the integral. In effect, in a lot of fields, people think of integrals as being things under measures, and they would put the Q of Z by the D of Z there. I mean, I'm not an engineer, so that freaks me out. But some of you may be very comfortable with the idea of integrating under a measure, and they even combine that there. And so the idea of an integral is what this is, and that allows Jensen's inequality to still be applied. Like this. So now the logs come beyond Q of Z. And the point about this now is that you can tighten the bound through changing Q of Z. And there's a nice way of showing that actually you can recover the truth. You can always recover the truth with a particular setting of Q of Z. And that's known as the EM algorithm. So in the EM algorithm, you do this effectively, but you have an E step and an M step. And in the E step, you set Q of Z to the posterior distribution of Z given Y. Once you've done that, actually probably this is on the next slide, so I was about to describe what that happens. So if you substitute that in there, that's what you do in the E step. So you set Q of Z to that, then actually it cancels in there. Why does it cancel in there? Because this is the joint distribution P of Y comma Z, product rule. Probability is so simple, isn't it? And then you're missing, for this to be the joint distribution, you're missing a P of Y. So when you divide in, what you need in order for that to be the case is a P of Y over a P of Y, right? That would cancel. And then that joint distribution would cancel, so you've got a P of Y in that function. Does that make sense? So that this is the joint distribution if I put a P of Y here, but then to put P of Y here, I need one up here. So I've got P of Y up here and down here now, but now that's the joint, that cancels. I'm just left with a P of Y on top. So if I do that, now this integral over Z doesn't appear in here, this integral over Z is just 1, and I'm just recovering the original equation. P of Y given over theta is equal to P of Y given theta. So the equality is tight, right? So actually, that doesn't get you anywhere. Because what people do with EM is they do it in 2 steps. They first of all set Q of Z to P of Z given Y, right? And then they have this equation, and that's typically a nice move if it's tractable. Like in mixtures of Gaussians, people do this. You set the posterior probability of the responsibilities of the Gaussians is what you set Q of Z to. And then once you've got that, you have this equation where the parameters only appear in here, the log of this, and you look at the expectation of the log of this under your P of Z given Y, and then you maximize that. But as you maximize it, your Q of Z becomes incorrect. So you maximize away from, so you change the parameters. If I change the parameters, I need to reset Q of Z again, because this actually depends on parameters. I should have it there. And so that's what you're doing in the EM algorithm. You do the E step, which is you set the bound tight, and then you maximize away, you maximize the lower bound, so the bound is now loose, but then you reset the bound tight. And that's the process of EM. And it's sort of a version of a variational approach. So, yeah, that's what I just said. See? I was right. Here's another way of looking at it, which is a nice way of thinking of it. That you can actually see that this bound, which I think people have started calling this bound the elbow. I always forget to call it that. Maybe that's a good name for it. The lower bound on the evidence, or something it means. But here's one of the ways I really like to think about this bound. This bound is now, this is the log likelihood, right? Expectation of the log likelihood under this approximate posterior distribution, and I've rewritten the next bit. I pulled the P of Z out alongside the Q of Z. So P of Z is the prior of Z, and Q of Z is our approximate posterior. This distribution is a Kullback-Leibler divergence. It's a measure of dissimilarity between distributions. It's like the, if you think about that, that's log P of Z over Q of Z. So it's log P of Z minus log Q of Z. So that's like a dissimilarity, and then it's the expectation of that under Q of Z. You can also look at the expectation under P of Z if you flip these things up and have the KL divergence the other way around. But here, it comes out of the mass that's under Q of Z. And this is measuring dissimilarity between the prior and your variational approximation. So it could be the posterior here, and then this bound to be exact. But it's just your variational approximation. So this is like a data fit term. How good am I going to get? Like if I made Q of Z a delta function, this would just be a maximum likelihood term. And this term says, don't make it a delta function. Because you want to keep it close to the product. Yeah? And actually, this will go all negative infinity. Nasty. And then, well, nasty things happen. You get terrible KL divergence. So what you want to do is minimize the KL divergence between the prior and this Q of Z while fitting your data. So keep the Q of Z close to the prior while making Q of Z predictive of the data you've seen. Makes a lot of sense. And I love it. Wow, let me say, I love it when a plan comes together. I mean, it's not when, but when maths comes together. I really don't like it when you write these things down and you make them up. I mean, fine, do that sometimes, but do that as a last resort. It's much more elegant when you're just applying bounds and you've got a handle on what you're doing, and then you've got terms that are quite interpretable, and variational inference very much has that. So I tend to use this statistical physics way of writing expectations, which is a bit confusing because people in machine learning also use it for infinite inner products in Hilbert spaces. But it's not an infinite Hilbert product in Hilbert space, it's a statistical physics expectation. So this is saying the expectation of Q of Z of this log P of Y given Z, and then this is just the Kullback-Leibniz divergence between those two terms. Okay. So, in some sense, that's an information theoretic interpretation of marginalization. Because in some sense, Kullback-Leibniz divergence is, what do they call it in information theory? Fernando, wake up. What do they call KL divergence in information theory? Information gain. Relative entropy is one term. But they also call it information gain, don't they? I think they also call it information gain at some point. I'm going to pretend they call it information. So this is like... Yeah, sorry. Yeah, wake you up and then tell you like a secret. So this is like the amount of information gained from Q of Z over P of Z. So it's saying minimize that, keep that low, keep yourself close to P of Z. But then this is an expectation of the likelihood under Q of Z. Okay. So yeah, how is it a variational method? Well, because we optimize Q of Z to solve the integral, and that's what gives us the variational method. Now, another thing we can note, another way of writing this down, which I guess is here, is this way. So this is our bound rewritten in the original way, not taking the Q of Z and the P of Z out, but written in terms of the bound plus, it's quite easy to show, because of that P of Z thing we had earlier, that the difference between the bound and the true log likelihood is this. This is the KL divergence between the true posterior and Q of Z. So if they're identical, this is 0. So KL divergence is always a minimum 0, and then unbounded positive. So what this is saying, okay, imagine pulling this back in. If I pull this back in, the Q of Z is the same, so this just comes into here. I get a Q of Z over a P of Z given Y. And the Q of Z cancels, so P of Z given Y makes this P of Y, and it doesn't matter what this distribution is because there's no Z left in here. So that's why that works. But this is the KL divergence now between the true posterior and your approximation. So you could still introduce that old KL divergence as well, but I want to focus on this different KL divergence, which is how far away you are in terms of the quality of your approximation to the true posterior. So this KL divergence tells us that the lower bound, which is just this thing, is given in quality according to how close we are. And we can't compute this in practice for an intractable setup because we can't compute this. So if we could compute that, we wouldn't be doing this, right? If we could compute that, we would be just computing it. And that's what we do with the standard Gaussian process. But what we're going to do here now is compute this, and if we simplify the form of this, so the trick is to use a simpler form for Q of Z in here than the actual form for P of Z given Y to try and make this tractable. So not all forms of Q of Z will work, but you try and choose one that makes the distribution tractable and it also gives you a tight lower bound. Okay, so that's that thing L. There's what some people call the elbow, and then this is the KL divergence between Q of Z and P of Z. Okay, so I'm going to stop there and just take questions on variational approximations, because that's general. That can be applied to anything. So, and Z, so very much what often happens, you'll see it gets a bit more complex in this, because in practice, you often have a lot of structure in the Zs, right? So P of Z itself may have all sorts of conditional independencies in it, right? And there might be all different types of Zs. You might call them thetas, and, I don't know, betas, and alphas, and all sorts of different mu's, and everything. And then when you see that, you'll see all those written out here. And then very often you'll see that the simplifying assumption is to assume that this distribution factorizes. So you might see Q of theta times beta, or theta times beta, depending on where you're from, times mu times Q of what. And then that will be the variational form of the approximation. Assume a factorization, and that will often make things tractable. So that's a typical way you proceed, but it still sits within this class, right? So that's the general variational inference approach. So questions on that?
So why is this called variational?
because instead of solving this, you do solve this integral actually. You can now compute these expectations typically under this Q of Z. You set it so that that is the case. But that integral is trivial to solve of these expectations. But you lower bound the original integral, which you can't solve, by maximizing with respect to this distribution. And that's what makes it a variational method. So variational methods are where you sort of take an integral and you replace it with an optimization, right? Which is a nice trick. Because optimization is easy and integration is hard. Other questions? This is classical variation. There are other variational methods, by the way, you can apply, but this is the sort of dominant one that you'll see. Classic variational methods. Okay. So everyone can now implement that for any model. Okay. So, sorry, my shoelaces are up. So let me just do my shoelace up. And then it would be while you gaze at my favorite graphical model. We talked about graphical models already. That's my favorite graphical model. There we go. This is my favorite one. It says that we have data, and somehow it's related to itself by a probability distribution, which is true. So no one can ever, so I have this talk I've done sometimes where I sort of say, it's funny, you know how people, there's that box quote, which is, all models are wrong, but some are useful. And then people always quote that, and then they show a wrong model, and like, as if it might be useful because it's wrong. That's the way it seems to me. So of course your model will be wrong, but it's the way that they sort of say, well, but all models are wrong, so mine might be useful as well. This is sort of funny thing. Okay, so this isn't a wrong model. This is correct, right? You can't deny this model. It's totally correct. There's a probability distribution over all your data. We haven't specified why or anything. This is actually another model that's impossible. Now, this is obviously I'm going to go for a Gaussian process here, right? But actually, if I don't specify I'm going for a Gaussian process, this is also correct. No one can ever tell you this is wrong because it's still completely general. It's just saying there's some latent variables. And of course, you know that I think of f as a function and y as an emitted likelihood from that function because we've done lectures on that already and I'm using the same notation. Here's the inducing variables idea. There's also some magical hidden observations that you never made. Right? So alongside your y, which you actually saw, these are the fantasy things you dreamed you saw, or the things that you may decide to store about what you saw. So they could actually be some subset of y, but they could be things you've made up. So you might never observe directly the Fourier spectrum of a function, but you might pretend you have in order to store it. And that's the inducing variable. And this is still completely general because, of course, we're just hanging things off f here. So this is still, there's nothing wrong with this model at all. We haven't specified these relationships. It's still totally true. And now we're going to play with this model a bit. So the first thing we're going to do, we're going to flip that arrow around. So I don't know if it's always the case that you can do that. It should be always the case. But it's not always the case that's going to be tractable. So certain distributions may not allow you to flip this arrow. But certainly in the case we'll look at with Gaussian processes, you can flip this arrow very easily. So I've now rewritten this distribution as a P of y given f, P of f given u, P of u. Okay? So my original thing is, if you think in your Gaussian process terms, this is just a Gaussian process. I've dropped x. X is up here somewhere, but it's not, we're not putting probability distributions over it. And the parameters of the kernel are behind it. But principally, I've got some latent variables, which is the actual function, which I never truly observe, and then some derived observations from it. And then I'm getting extra derived observations from it via u, and I haven't specified how that's going to happen yet. So I'm going to invert that arrow, and then pull out, by inverting that arrow, that allows me to write things in terms of P of u times P of f given u times P of y given f. So I've got a bit of a chain going on now. So I can rewrite it as a chain. And now I'm going to drop u. So now I'm going to ignore u for a bit. So we're going to leave u behind. Kind of condition on u as if you've seen u. Drop it out of the equation. So I've now got an equation like this. So this is basically the posterior for our Gaussian process. It would be the posterior distribution over our Gaussian process as if we'd observed these inducing inputs. So it's like, these are the things we've chosen to store, and this is the prediction we would make if we'd chosen those things, and then this is the likelihood, which is going to turn out to be factorized. Look at that, that was well timed. So we assume that the likelihood is factorized. So in the first place, I hadn't assumed that the likelihood factorized could be very general. And there's often occasions where you might want to have a very general likelihood like that. You don't always want to assume it factorizes. But certainly for this approximation, we're going to assume it factorizes in some way. So here, across the data. So this is exactly what we've had before, and typically we've been saying, well, this is Gaussian noise, but it could also be a sort of probit function to give us a classification or whatever. Now, what I want to look at is this object here. This is the conditional likelihood on U. Now, just to give you a bit of a leading point about where we're going with this. Remember I've got P of U. Remember that U is fixed dimensional. Actually, I can change it whenever I like, but in theory, it's the number of inducing points I choose, right? It controls the quality of my approximation. So P of U does not increase with data unless I choose to increase it. I control it. It's totally within my power. Now I'm starting to write something which is a non-parametric model in terms of a P of Y given a fixed dimensional vector. And I've already dropped the prior over the fixed dimensional vector. So I'm pulling this model back towards something that looks more parametric. It's going to end up, so I've dropped the P of U, but this thing here looks like it's in a form which looks like a parametric model. And that's the key trick, because once you've got it in a form like a parametric model, any trick that people apply to speed up parametric models, you can apply. So stochastic variational inference, parallelization, whatever. So we're going to look at the log conditional, and what we're going to do is introduce a variational bound. So this is just what we were playing with before, conditioning on U, but the variational lower bound is going to be over F. So we introduce Jensen's, and that gives us this form. The integral of Q of F, so this is our variational approximation to F, over this joint distribution here, which is the P of Y given F times P of F, ignoring the conditioning on U. Now we're going to do a weird thing. This is what Michaelis, this is Michaelis, trademark Michaelis. Very cool, this. That. What do we do? Watch closely, people. We did two things there, actually. Oh, it says at the top. We set Q of F to P of F given U. This is very, very unusual. It's normally like a dumb thing to do in variational inference because you're setting your posterior to equal your prior. Right? There's the prior. There's the posterior. We're setting the posterior to equal the prior. So we're actually zeroing out that KL divergent set. So this is why Michaelis is one of these great thinkers who sort of, I mean, I was trying to get him to do sampling in this system, and he came back and said, oh, well, but why don't you just do this variational trick? It comes up, oh, yeah, so it does. Yeah, why is it a good trick? So it seems dangerous. And it would be dangerous if it was a normal model, but we control U. Right? As part of the variational approximation, we're going to end up controlling U. We'll see that in the end. So because we control U, this isn't the prior, this is the posterior given our fake observations that we've invented, right? We get to make them whatever we like. So we're actually making the posterior approximation to Q dependent on these fake observations, which is a really nice trick. Now, what that means is we immediately, these expectations are typically, sorry, for the Gaussian case, they're trivial. Trivial expectations. So this expectation of the sum of the log P of yi given fi, that's now trivial. So you can compute that straight away. And it has a sort of form like this. Obviously, it comes into the sum. So you've got this sum of the expectation log P of yi given fi under the P of fi given u. So right, obviously when I pull this into there's only fi on the side here. So across the sum, all the f's integrate out apart from the fi one. So this thing in here becomes P of fi given u. Now that's key because P of f given u itself is difficult to compute, but P of fi given u is not difficult. So we now have a lower bound on P of y given u. And the difference between this bound and the truth is given by this KL divergence. Now this is why we think of it as variational compression. Because if you've got the same amount of information in U as you have in U and Y, then this is exact. So for example, one way to make it trivially exact is to set U to be Y. But that doesn't give you any computational advantage. But if you manage to find a set of U's that tell you the same amount of information you have in Y, this becomes exact. And then you recover the original Gaussian process. So the information in Y, when you optimize the lower bound, you're compressing this. So when you maximize the lower bound we're going to get, you're minimizing this KL divergence. So you're pushing the information into U. You're doing exactly what you want. Trying to push all the information about the data set into U. It's a really elegant thing. So for the Gaussian likelihood as well, you get this effect. So this is like something like I called collapse variational inference. Did I in the first time I did it? No one noticed when I first did it, and then other people I think called it collapse variational inference. That's right. And then we had a paper on something related. But you basically, if you do this expectation here, you can turn it back into something that looks like a Gaussian if you have this corrective term on it here. So this term is the, like within the Gaussian, within the log Gaussian it's quadratic. I've rewritten the quadratic out, but the expectation has an expectation of f squared on it, right? So you have to pull that term out and subtract off fi squared from here, which allows you to rewrite the quadratic term here. And then this point, this is the variance, this is the posterior variance of P of f given U. So this is the mean of P of f given U, and this is the posterior variance of P of f given U. So this is the way that this lower bound looks like. And of course, if we exponentiate it, that's a log lower, that's a lower bound on the log P of y given U. If we now exponentiate it, then it looks like a Gaussian. So this bit here, e to this, is a Gaussian with mean expectation of fi. And then there's this correction term. So you could write that separately. So that's what we're going to do, I think, on the next slide. The P of yi given U has this form. It's a Gaussian distribution times this correction where I've defined that to be Ci. Okay, what's really cool about that, let's see if I've written down there. Oh yeah, so you can compute all these terms. Like, so the Ci is that form, and that's the posterior variance of the P of f given U for the ith point. So that's just the standard Gaussian process equation. And we notice it's not a function of U, but it is a function of the inputs to U. So it's not a function of the values of U itself, but it's a function of the inputs to U. This, on the other hand, the mean function of that is a function of U, because the mean is this, right? This is the standard Gaussian process mean as if we observe U. Expectation of f P of f given U has a U in it. So there's a U inside here, but there ain't no U inside Qi, right?
So if the U is fake data, where do you get the inputs to U from? Or how do you know?
They turn out to be variational parameters.
As well. Okay.
As well, yeah. Good question, yeah. So x, yeah, I'll come to that in a moment. So in order to do this, right, we're defining a few different things. This posterior over U we must define a prior distribution over it. So actually, I should have made that clear. I should write a slide on that. And maybe instead of a slide, I'll just write it on the board. KFF, KFU, KUF, KUU. That's what we say is the joint distribution over F and U. So it's a joint Gaussian process. So we have to define the cross-covariance and the covariance. And this is where we can make them derivatives or Fourier coefficients or whatever. And of course, inside these things are XU. So that all needs to be defined to give us the relationship between F and U. And that's the way we do it.
So do we need XU explicitly or only as they appear in the kernel?
Yeah, you tend to need it explicitly. I played with this. It's a good question. I played with this a bit and showed that PCA is an example of this approximation where U is your latent variables. You can do it in that sort of case where you just optimize over these kernels in free form. That was an experiment in that type of idea. But in general, you can't do that because this matrix has to be positive definite. So the easiest thing to do is to ensure that it's a joint Gaussian process with your f, and then you know that this joint covariance matrix is positive. And that's how we tend to do it. Other questions? Okay, so let's bring back the prior. So the prior, as you can see from what I've just written down, is a Gaussian process over P of u. And if you put it back in here, this is the cool bit. This thing here is an independent model. I've written it as a single Gaussian. So there's a product over these CIs. I've written this as a single Gaussian because I'm writing it in, or am I writing it in these terms? The way I should write it for you is this way, right? Because you've seen this lots of times. So what this model says is, it's a sort of, well, it's not the model, it's the lower bound on the model. But if you look at it, it looks like a model that is saying that y is equal to k f u, k u minus 1 u, plus sigma squared, so plus epsilon, where epsilon is drawn from a Gaussian which is zero mean and spherical variance, like that. This is what we just keep writing down. This is, there's no expectation under this one. We've got P of u now, we're going to reintroduce P of u, but now P of u is a Gaussian with zero mean and covariance KUU. Normally it's like diagonal. This looks like those parametric models from before, but with some funny covariances in. And then when we multiply this out, we want to say what's the marginal distribution over y as a result of this. Well, it's on the next slide, but before you can think about what it would look like, it's obviously going to be KFU, KUU inverse, KUU, KUU inverse transpose, which is just KUU inverse, KUF. So that's what you get. So when we were doing this in linear models yesterday, we kept on getting WW transpose here. But the W in this case, it's not WW transpose, it's KFU, KUU inverse, KUU, KUU inverse, KUF. So one of those KUU inverse cancels, and you get this form here. So this is the lower rank approximation to the Gaussian process. It looks like a Gaussian process with this funny lower rank approximation. But it's got this correction term. So it's a bound. If that were a Gaussian process on its own, it could not be a bound unless it was exact. It's not a bound, it's an equality. Because of the normalization. You can't lower bound the probability distribution to the probability distribution at all points, because they're normalized. So this corrective term here forces it to be a lower bound. That's amazing, because if you find this corrective term is a product of worms, which sometimes it is, you know the lower bound is exact, and you never see that in variational approximations, having that sort of quality control over when it's exact. You never know when that's going on. There's a reason for that, which I won't go into in detail. But that's a really elegant thing. So it looks like a Gaussian process, but because of this, it's a lower bound on the Gaussian process. And almost all Gaussian process approximations can be seen as related to this. Okay, that was a long way to get to a point in terms of what we want to use this for. So in practice, what you do is you optimize this thing with those correction terms on, instead of optimizing the model directly with respect to the parameters of the kernel, the inputs to x, the locations to x do not appear in this. They do if you do stochastic variational inference, because in stochastic variational inference you don't do this integral. So in stochastic variational inference you leave this integral alone, and you do stochastic variational inference on this object, and you sustain a posterior distribution over Q of u. But we can collapse this integral out. When you parallelize, you collapse this integral out. But rather oddly, the main reason I wanted to introduce that, which is an interesting thing to talk about, was also because it allows me to get to, over there, that's a little comparison between what this model is looking like and what a standard basis function model would look like. Yeah? So this is why we can suddenly apply all these approximations and do lots of grading things. GPy does all this stuff for you. It's quite, the maths is quite nasty and involves lots of chromatic products and stuff. Okay, so I'm short of time. I just want to skip through onto this and sort of say, well, without giving you the details, this is what makes deep Gaussian processes possible. Because that is our new lower bound on the Gaussian process over U. But what also Michaelis realized as well is if we want to integrate over Z, where Z is now our inputs. Remember we had quite a bit of a shift of notation for the deep GP, where we're saying Z is our inputs to the covariance function. probably I should have kept it as x. So think of this as x if it's easier. We can actually compute this variational lower bound as well. So this is the variational lower bound on the lower bound. So that's our lower bound, and now we can apply a variational lower bound to it, and without going into too much detail, why can we do it? KFF inverse has disappeared. X only appears in KFU, and it actually appears in C as well. But it only ever appears in the kernel function directly. And it turns out, because of the log here, if we can compute expectations of that covariance function under Q of Z, we can compute this lower bound. And that's the secret behind deep Gaussian processes. So, just pushing on quickly, the deep Gaussian process is allowing, this is an example of one, just mapping from a Gaussian, from a square to this, to this, to this, with Gaussian processes each time. So we're using that trick recursively. So we apply that bound at each layer. Because once you've done it for this layer, that's the first thing, you can do it for all layers. You can just push it all the way up. And you can have as many layers as you like. And you're now pushing the uncertainty everywhere. It's really cool. So this is work, the original paper is by Andreas Damiano. And I'm just going to show you this sort of thing, finish on, I have to do a switch of computers. Now, let me check if that's going to work. So yeah, this is the sort of thing we try and do with it. While I get the demo up. So this hierarchical model here, in the hierarchical GPLVM, as we used to call it then, is now something we can do where we optimize over all the kernel parameters. And because of tricks like ARD, which again I haven't talked about, we can actually learn structure. So we can learn the structure of the model now. Now I'm not doing it in this example, but I'm going to do it for some digits. So these are actually ARD parameters, which are switching on and off layers in digits. But the example I want to show you is this one. So this is the lowest level, two-dimensional. This is a 17-dimensional latent space that is governing a USPS, no, an MNIST digit data set, I think. I can't remember if USPS or MNIST, but it's a small data set, it's only 150 digits. Because the point here is we wanted to show that deep learning was valid even when data sets are very, very small. So there's 17 dimensions in this lowest level, but we were able to show using the variational lower bound that a 5-layer model was justified in modeling this data. So 5 layers of depth was justified. And what I'm going to show you is, as I move around these latent spaces, what the digits look like. So Andreas has chosen a point in this 17-dimensional space which is like a 0, and in these 2 dimensions of this space, you see you get very detailed changes on the 0 going on. And now what we're going to do is go up on there, and he's chosen a point that looks like a 6. This is 1 layer above, and this one is 14-dimensional, or maybe 12-dimensional actually, because this would be showing 2 of these dimensions. Oh no, I think it's 14. 14, yeah, because there's missing. It's the 2nd dimension and the 6th dimension. Where in these dimensions, it seems that the latent variables are controlling the shape of the 6. It's quite nice. And then the next layer will go right to the top, which is the 5th layer of the model. And now, because there's 6s, 1s, and 0s, that's what the data set was. Very nice generative model of 6s, 1s, and 0s from only 150 data. Of course, these models work really amazingly well in low data because that's where the GPLVM also works, and yeah, that's very nice. So we were very pleased with that, and the big thing is to try and scale that up to much larger data sets, because the real interest is trying to do the sort of things people want to do with graphical models. But with this sort of form of structured learning, and with, let's see if I've got something. Oh yeah, that's that example. So the nice thing about this is it's learning the number of nodes in each of these hidden layers. So these nodes are switched off, these nodes are switched off. So it started with like 20, but it only used like, I don't know, 18. And in this layer it's only using 1, 2, 3, 4, 5. This layer it's only using 1, 2, 3, 4, 1, 2, 3. This layer it's using 1 plus 3 very small length scale, which means they're broadly linear. So we were looking at these 2 dimensions when we moved around, where most of the variance was. I think That's it. So they're very promising models for unsupervised and supervised, easily adapted to handle multitask learning. We do a lot of that. And multi-view learning, very easy with these models. They can also do supervised learning, very general framework. Data dimensionality is not a computational bottleneck. I didn't demonstrate that, but it is the case. And variational compression shows promise for scaling these models to massive data sets. I mean, we had a question about that, and it is true. There are big engineering challenges with doing that. Bear in mind, it took them a year to get that ImageNet result. And that was with all the knowledge of neural nets that people had accumulated up until then. So it's, it's likely to take us time because these algorithms are certainly more complex. And there's some references, and that's it. We're very short on time for questions, so just going to take one or two.
So when we go from one layer to the next with the variational approximation, what does Q approximate now?
It approximates, so we have an independence, yes, implicitly it was independent from the way I showed that we're applying one layer. Let's get that model up. You have a Q of Z at each layer, you assume independence for them. And then you've got a Q of F, which is being collapsed out at each layer, which is the Q of F given you. You're not quite assuming independence for that because it's dependent on U. And then you've got Q of U at each layer, which is assumed independent. So it's quite a strong factorization in the end. Yeah, I mean, the trouble with sampling in these things is the correlations are awful between the different layers. So I think you can quite easily do a sampling algorithm using what's it called, STAN. So I think Michael Betancourt does an example where you can sample the deep GP or stack GPs with STAN. I think for large data it could be quite difficult, but it'd be great if people get it to work. I should say Rich Turner's coming up with some great algorithms with his, student whose name escapes me, Thang Gui, and someone else too. Various people in Cambridge are doing a lot of interesting approximation algorithms that are related to ours but different for these deep GPs. So I'm hoping we're going to see a lot of progress in that.
And then in the end, what's the distribution of the Qs? Is it?
We assume, yes, sorry, further good question. We assume that it's Gaussian and Gaussianity on each one to get the tractability. If we don't do that. We have other models actually where we've been trying to do, we've done with Zhenwen, infinite buffet process priors over the latent spaces. So effectively our Q distribution is an IDP, and we can do that as well. But for the deep GP, we force it Gaussian. In that IDP case, we obviously have different.
How do you decide the appropriate size of layers?
The size of the layers. Actually, well, we just initialize them and then it learns them. So there's very little, there's actually shockingly few parameters in this model. So you set them up initially, you have to start with something. But there's this approach called ARD where effectively you could switch off, and it works really well in this model. So you start with a number like 20, and then as you train, one of the kernel parameters actually starts to remove ones that aren't being used. And we see it does that quite effectively. So you try and start with something larger than you want, but of course that's awkward. You'd rather start smaller than what you want. And then the depth, actually it will switch off layers above if they're not needed. So it will switch off entire layers. And in fact, one challenge when you're doing the optimization is to make sure it doesn't switch off the layers too quickly. Because if you initialize it badly, then the first thing it will do is switch off all these layers because it will score well between, remember the KL divergence between the prior and the posterior approximation? At initialization, it can make that 0 by setting the posterior approximation to the prior and switching off all the layers. And it will tend to do that.
So as a way of deep learning.
Huh?
So as a way of deep learning.
Yeah, well, yeah.
It's a program.
Yeah, we don't seem to have as many problems as they have because Andreas got this working very quickly right off the bat. And it took them a long time to get those models working. But we do have problems scaling them up to large. And I think with stochastic variational inference, it's quite hard. So then you start getting quite serious difficulties because you have real challenges over your updating schedules between the Zs and the Us and various other things. And we've not worked that out. That's why we're going for parallel. No, dropout's totally unnecessary. You don't want to do that. Yeah. Dropout's like a, in fact, you can show that dropout is, so Yaron has this nice paper that shows that dropout makes a deep neural network approximate deep Gaussian process, right? And if you look in that paper there, it's all about quite a bad variational approximation. It's a very strange variational approximation that uses to do it, but it's a variational approximation to a deep Gaussian process. So we don't use dropout because it would be a bad one. It's, they use that for regularization. We're Bayesian. We've integrated out all the parameters. We don't have to worry about overfitting in that way. So, no dropout.
Okay, so can you design the cycle plugin using the processor?
Using Greek? Yeah, no, we'd like with IBP. So we've been trying to do that. But our paper, which is doing it on a one-layer model, keeps getting rejected. So we want to do it on the one-layer model first, and then do it deeper. But we keep getting rejected on the one-layer model. So, yeah.
And has the GPLVM been applied to text data?
No, it's not. It would be great to, actually. The reason why people, I think, don't do as much is because the likelihood's a little bit awkward. It would be really cool to. It would work in an interesting way. I'd love to see it done. It's not to my, oh, no, someone is doing something with it. I can't remember who it was. I was told about someone trying to do, oh, maybe it wasn't text data. Putting a GPLVM on top of an RVM, or something like this. I can't remember if it was text data. But that gives you binary. Yeah, because the challenge is the likelihood, if you do the likelihood properly, it gives you a bit of extra work to do and some computational headaches. So I'd like to see it, but...
You mean the multinomial as a likelihood? Or
yeah, you do the multinomial or whatever. Yeah, so you have to put the multinomial out here. And that, you know, multinomial means that you're getting processes for each output, which is a lot of work for not much increase in modeling power. So I'm not quite sure what the best way of doing it.
So can I have a simple question? So what comes next? Deep.
What comes next in the world of deep?
Yeah.
That's not a simple question. That's not a simple question. I don't know. You know what's really annoying for me, actually? It's great, but it's annoying as well. I'm in two minds about it. I think it's great that these models are so successful and that there's all these interesting things being done that are practical, right? So that means we've got a massive influx of companies because you can do amazing things with images and with speech and time series and language with these neural network models. But we're going to hit a wall. We're going to hit a wall because all those setups have enormous amounts of data. And all the big companies are recruiting large numbers of people to label data because that's what you want. Massive labeled data sets and then train these models. That doesn't work for things like health. So health data, you can't force people to become sick in an effort to get more training data for your deep learning model. It's considered unethical. But yeah, so I think I focus on data efficiency as a big thing, that these models are incredibly data inefficient, the ones that you see in the wild. These models are very, very data efficient, but we're having trouble scaling. So I think more focus on data efficiency. The thing also that frustrates me a little bit about the whole deep learning thing is, you know, I've always, Jeff Hinton, when he talks about it, and has always talked about it, he wasn't talking about neural networks being trained for supervised learning. He was talking about unsupervised learning and interesting different structured models that in the early days were all graphical models as well, deep hierarchical graphical models. And it's a little bit worrying that we're just so obsessed at the moment with supervised learning. I'm hoping it will fade a bit, but you don't know. When you've got 4,000 people coming to NIPS, and you only had 3 years ago, we had like maybe less than 1,000. You know that 3,000 of those people only care about fitting neural networks to very large image data sets. Which is a bit of a lie. Yeah. Other questions? Okay. So I'm already overrun. Sorry. Quite badly. You should have stopped me.
Let's do a 10 minutes break.
Yeah, 10 minutes.
Okay. People are shouting with you that I don't understand.
Thanks very much.